Hello everyone. In this video, we're going to be solving a sequence problem. We have 2, 5, 10, 18, 30, and so on and so forth. So we have a sequence of numbers that follow a certain pattern, and we're going to try to find that pattern. And of course, once we find the pattern, we can find the next term, we can find the 10th term, we can find the millionth term, so on and so forth. But the whole idea is built around finding a formula for the nth term of this sequence. Okay? All right, let's go ahead and take a look. Obviously, when you get a sequence like this, there are so many possible answers, right? And this is usually not well defined. You've probably seen those, IQ type questions on social media where they ask you a problem and if you solve it, you're a genius, so on and so forth. They're just garbage. But anyways, for this problem though, we actually have a pattern that works. But how do you know that's the only one that works, right? Obviously, you can find more than one. But what is meant here is going to be an easy one. So how do you find these kinds of patterns? First of all, you look for certain things that are super obvious. You never know, right? It could be a geometric sequence. It could be an arithmetic sequence. Let me go ahead and give you some examples so you get the idea if you're not familiar with those. For example, if you have a sequence that works like this, 1, 4, 7, 10, 13, hopefully you get the idea after a few terms. There's no guarantee that this is going to continue the same manner, but we're just assuming that things will go well. And you probably noticed that every time we're adding a 3 to find the next term. So this is called an arithmetic sequence, okay? Because there's something called a common difference. And that's called the D. There are formulas, so on and so forth. Hopefully you know those. And there's the geometric sequences. Like, for example, you can start with 4, and then 2, and then 1, and then 1/2, and then 1/4. You get the idea? Every time we're multiplying by 1/2. Obviously, we don't have to multiply by a number that is greater than 1. We can even multiply by square root of 2, which is going to give you some interesting sequences, such as, let's say 1, and then root 2, and then 2, and then 2 root 2, and then 4, so on and so forth. You see, that's the whole idea. And in these cases, we do have what's called a common ratio. So for the arithmetic, and these are geometric, by the way, for the arithmetic, if you divide a2 by a1, a2 representing the second term, you do, I meant to subtract. If you subtract the second and the first term, you get a common difference. For the geometric, if you divide a2 by a1, you get a common ratio. Those are well-known sequences, but is it one of them? No, not necessarily, right? Because if you look at the numbers, you get 2 to 5, that is a plus 3, and then you go 5 to 10, that's a plus 5, and then you go 10 to 8, which is a plus 8. Could this be a clue? 3 plus 5 equals 8. Could be. Who knows? We got to keep checking. And then the next one is plus 12, and guess what? The magic is ruined here. So it's not like that. Obviously, that's not going to be a good pattern if it did, but what is this telling you? First of all, this is telling you that the increase is not constant, but do not give up, because you can also, you can find something from here, but I'll show you how. But before we do that, how do we know that this is going to increase by the same amount, right? In this case, it doesn't. Well, it could also be like something like maybe we multiply by something. Take the 2, multiply by 3, and subtract 1. So kind of like 3x minus 1. Could that be the formula? Well, it works for 2 to 5, but it doesn't work with 5 to 10. Because if you triple 5, you get 15 minus 1. It wouldn't work. So it kind of fails. And a lot of times, patterns that you guess are going to fail, okay? Could it be something like this maybe? Because this is 1 plus 1, so it's 1 squared plus 1. And this is 2 squared plus 1. Okay, that's pretty misleading. This is 3 squared plus 1. So we're getting our hopes high, right? But then when you get to the fourth term, this is not 4 squared plus 1. Unfortunately, that rule breaks one more time. But are we getting closer? We're finding more and more terms that fit a certain pattern, but unfortunately they break. So at least we do know that our pattern has to work for 5 of these numbers. And if you can find one that works, you're fine. If you find another one, let me know, because I'd be interested. There will probably be more terms. And I can also show you, actually, I do have an idea. I can show you after we find the idea that is meant to work, we can find more ones, okay? I'll show you how to do that too. There's a way to work it. Even for something like this, let's say 1, 2, 3, 4, 5, and how many terms I gave you? 5 terms, okay. What do you think the general rule for the sequence is? Do you think it's an equals n? Well, it looks like it, but at the same time, it could also be something like an could be n plus, now take a look at this real quick, n minus 6, n minus 7. Why does this work? The reason why this works is because for n equals 1 through, wait a minute, did I? Okay, that's not what I meant. I meant to write something like this, I guess. N plus n minus 1 times n minus 2. Oh, yeah, okay. I'm supposed to write the whole thing. Never mind. 1, 2, 3, 4, 5. Oops, yep, that's what it is. Okay, that's a quintic. Wow, that's crazy, isn't it? Now, the reason why this works is because for n equals 1, we get a 1 equals 1, because everything here cancels out. You get the idea? For n equals 2, we get a 2 equals 2, a 3 equals 3, a 4 equals 4, a 5 equals 5. Unfortunately, it works. But what about a6, right? Without knowing a6, you can't tell. Because with a6, we're going to get a completely different sequence. You get the idea? So there's a way to generate more and more and more sequences. But if you have something that's kind of less trivial than this one, let me know. So let's go ahead and clean it up, and I'm going to show you how this works. So we're going to go on differences, okay? And when we looked at the differences, we did not get a pattern right away. But again, do not give up, because the answer might be super close. So let's go ahead and take a look at the differences again one more time. But this time we're going to be more careful. So from 2 to 5, it's plus 3, plus 5, plus 8, and then plus 12. Okay, we have enough evidence to conclude with something. So here's what I'm going to do next. Instead of sticking to the first difference, because it didn't really give me something helpful, I'm going to go to the second differences. What does that mean? The difference of differences. From 3 to 5, that's a plus 2, that's a plus 3, that's a plus 4. Uh-oh, looks like a pattern is emerging, don't you think? Now, what happens next is actually mind-blowing, because this is like a plus 1, and this is like a plus 1. Beautiful. If I gave you a little bit more terms, I think that would be more convincing, but at least you have an idea. Okay, based on what we're given, the third differences, these are the first differences, these are the second differences, and these are the third differences. The third differences are constant. What is that supposed to mean? Well, when the first difference is constant, then that means you have a linear sequence. An is something like an plus b. If the second differences are constant, that's quadratic. When the third differences are constant, that is cubic. You get the idea? So we're going to assume that our sequence a sub n looks like this. An cubed plus bn squared plus cn plus d. And then we're going to plug in all these numbers, okay? For example, n with 1, a1 equals a plus b plus c plus d, and we know that a1 is 2. If you replace n with 2, you're going to get 8a plus 4b plus 2c, or not 2c, plus d, and that is going to equal 5, as you know. And then a3 is just going to be 27a plus 9b plus 3c plus d, and as you know, that's going to be an 8, right? I mean 10. And then a4, we only need 4 equations, don't we? 4 cubed is going to be 64a, and then 4 to the second power is going to be 16b, plus 4c plus d, and that is going to equal 18. Now, this is a linear system of equations. You can solve with matrices, whatever you like. Doesn't matter, but I'm going to give you the number without further ado. From here, a is going to be 1 over 6, b is going to be 0, c is going to be 11 over 6, and surprisingly, d will be 0. Who could have guessed, right? So a sub n can be written as 1 over 6 n cubed plus 11 over 6n. You could also write it as n cubed plus 11n divided by 6, because this is the same thing, right? No, so if you go ahead and replace n with 1, n with 2, you can n with 3, you're going to get all these numbers. But let's go ahead and try one of them randomly, like a equals 3, 27 plus 33 divided by 6, that is 30, 60 divided by 6, and that's 10. And in fact, I meant n equals 3, not a equals 3. Of course, this gives you the third term as 10, as you know. So from here, if you wanted to find the sixth term, the next one, that would actually be replacing n with 6. You're going to be able to find that it's equal to 47, and that should also fit the pattern. But we achieved our goal, and that brings us to the end of this video. Well, thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care. Don't forget to check out aplusbi, a channel that I made that focuses on complex numbers. And until next time, bye-bye.